modern physics portion which is common to JEE Mains and JEE Advanced. So now there are some additional topics in modern physics as well as optics which are exclusive to JEE Mains. So we will get into a discussion of those topics. So I will give you a list of those topics also. But to begin with, today we will discuss with some questions pending in as doubts in wave optics, and as we discuss those, we will get into the remaining topics from optics which are for JEE Mains. So we will start with questions and doubts from wave optics, okay, which I'm going to get into now. So last time you had sent me some questions from H.C. Verma which we were not able to complete because we were in nuclear physics and we took the entire lecture in discussing that. So we will start with the discussion of those questions. Yes, Aditya, I have those questions written down and others also. Okay, so I will discuss those questions. So let's start with the wave optics doubts today. Then I will tell you the plan for the remaining topics that we are doing. So we'll start with the questions that were asked as doubts from H.C. Verma, and a couple of questions that otherwise also I want to discuss. So we'll start with this question number 28, which is slight variation of the standard YDSE setup. Okay. So question 28 of H.C. Verma is basically a situation like this, that we have something similar to the standard YDSE setup, but instead of 2 slits there are now 3 slits involved. So there is slit here, slit here. Okay, so there are 3 such slits, A, B and C, and they are at a gap of D and D respectively, and this is capital D. Now there is monochromatic coherent light incident on the 3 slits, presumably coming from another single slit, okay, which is illuminated by a monochromatic source very far away. Okay. So there is coherent monochromatic light. Of wavelength lambda illuminates the 3 slits A, B and C. Now this point in the screen here is labeled as P0. Okay. So it is given that BP0, given the distance BP0 minus the distance AP0, is lambda by 3. So this is lambda by 3, and also given that capital D is very large compared to lambda, which means that small d is also very small compared to lambda automatically. Okay. So we have to, so first of all we have to find the relationship between small d and lambda. Okay, and the other thing is that if each slit produces an intensity of equal intensity of I on the screen, then what is a net intensity? Okay, so if each slit produces equal intensity of light I on the screen, okay, obviously this thing being the screen, we have to calculate the net intensity at the point P0. So this is the question. So this is a very simple case of the phasor addition of light coming from three sources. Okay, so we'll have to assume that, given the waves of monochromatic light being parallel and coherent, we have to assume that the three sources A, B, and C, they act like coherent sources which are in phase, because there's a parallel wavefront that hits them simultaneously like this. Okay, so that means light coming from the three sources A, B, and C, the three sources, the secondary sources A, B, and C, or the slits acting like secondary sources, themselves are coherent. There's no phase difference. So the net phase difference of light reaching any point on the screen is nothing but the path difference converted into phase difference. Okay, so the phase difference created is only because of the path difference. Okay, so the first part is of course a geometrical calculation. We have to just find this thing. So you can see that geometrically the quantity Bp naught minus Ap naught is nothing but this thing. It is capital D square plus small d square minus capital D, and this is given to us as lambda by 3. Okay, and it is given that capital D is very large compared to lambda. So this also means that capital D is very large compared to small d. Okay, because you can understand that in this relationship, okay, the difference of these two is going to have something to do with the d by d ratio, small d by capital D ratio, and that is comparable to lambda by 3, and lambda is very small compared to this, so it automatically implies this. Okay, so let's solve this now. So if you take capital D common here, 1 plus d square by capital D square to the power half, this is lambda by 3. So further we can take capital D common and write this as the power half minus 1 is lambda by 3. Now we can use this relation that d square by d square is extremely small compared to 1. So use the binomial approximation next step. So this becomes, so next step becomes an approximation here. So let's use the approximation symbol. So the power comes inside with the approximation. Okay, so 1 and 1 cancels and we have d square by 2 times capital D is equal to lambda by 3. So we can see that small d is equal to square root of 2/3 of capital D lambda. Okay, so this is the first part. Now we will use a similar method of approximation using the binomial approximation concept to come to the second part, where we'll see the phase difference between light coming from A and B, and then the phase difference between light coming from B and C. Okay, and from that we will calculate the net intensity. But make sure you're clear with this part first, all of you. Okay, so next we have to calculate the intensity of light reaching the point P naught, the net intensity. Okay, so before we start the next part, we have to understand this thing that I told you, that the slits A, B, and C will act as coherent, monochromatic, and in phase secondary sources. Now why they will act in phase is because the light reaching them, the parallel beams, the wavefronts are such that the same wavefront at a point, the same wavefront is simultaneously hitting the slits A, B and C. So there's no phase difference between the wavefront hitting the point A and the point B and the point C at a given instant. So that's why as secondary sources they are in phase. So that is why the light reaching any point on the screen from A, B and C, the phase difference is only because of path difference. There is no inherent phase difference between the sources. Okay, so that's why they act like in phase sources. So this will be taken into account when we come to the second part. Okay, so with this, let's consider the second part of the question. These beams of light, we have to calculate the phase difference between them. So this is the idea now. So the phase difference between the light from A and B, let's say that is alpha. So alpha is equal to 2 pi by lambda into this path difference. Okay, and similarly the phase difference between light from, let's say, A and C, if we consider that, okay, that is beta. So beta is 2 pi by lambda Bp naught minus, sorry, Cp naught minus Ap naught. Okay. You can also consider B and C, but I have considered A and C because I'm going to go with the phasor diagram method. So that will be more important for me. Okay. Now remember, it was given to me that Bp naught minus Ap naught was lambda by 3. This was given, and we had worked out that this relationship was actually this. Okay, that d square by 2d had become lambda by 3. So this is going to be the important relationship for us when we are considering this. Okay, so from this above information we can see that if we substitute this here, we can see that alpha is equal to how much? It is 2 pi by 3, or that's equivalent to 120 degrees. Now let's find out what this is. Okay, so similarly Cp naught minus Ap naught is square root of capital D square plus 2d whole square minus p is this quantity. So same treatment we will do. Okay, we'll take the capital D outside. So this becomes square root of 1 plus 4d square by d square minus 1. So now 4d square by d square is still very small compared to 1 because capital D was very large compared to small d. So approximation step, okay, 1 plus 2 times d square by d square minus 1. So this becomes 2d square by d. So Cp naught minus Ap naught, this quantity becomes this. Okay. So now you substitute the information that we have above, this information here. Okay. So this is becoming 4 times lambda by 3. Okay. Okay, so that means beta, which is 2 pi by lambda, is equal to 8 pi by 3. So that is, okay, so that is the same thing as 120 degrees. So that's how we understand that actually the phase difference between light coming from B and C is just 2 pi. That is why from A and C it is 2 pi plus pi by 3, plus 2 pi by 3, right? So now that we have got alpha and beta, so we know alpha is 2 pi by 3 and beta is 2 pi plus 2 pi by 3. So we realize actually that the rays coming from B and C are having a phase difference of 2 pi only. So they are in phase actually in that sense. Okay. So now when we are doing the Phasor addition, so suppose the amplitude from sources A, B and C is E naught each. So the intensity from each one is proportional to E naught square. So this relationship. Okay. So now what is happening? The net intensity at the point P naught, of course, that will be the phasor sum of amplitudes. So that phasor diagram now will look like this. That phasor diagram will look like this. If this is the amplitude of light coming from the source A, then the light coming from the source B will be of same amplitude and magnitude but with a phase difference of 120 degrees. So this is 2 pi by 3. And the third one will also be the same direction, because okay, so this is your alpha, and here if I try to trace the value beta, yeah, so if I try to trace the value beta, that will be like this. So it's actually one full round plus this. So beta is 2 pi plus 2 pi by 3. So this is from the source C. Okay, so you can see that it is that sort of triangle, x 2x 120 degrees. Okay, so this sort of thing it will happen. Okay, so with your understanding that it is that particular triangle we are talking about, see that the net amplitude will become like this. It will be root 3 now. Okay, so once you have recognized that the phasor summation is giving us the net amplitude like this, you can see that therefore net intensity being proportional to net amplitude square. So I net is proportional to this, whereas I was proportional to. So you can see the net intensity will become 3 times the intensity from any single source. Okay, so this is a very typical kind of example of a variation of standard YDSE question. Apart from, of course, the variations we have discussed earlier, where you have the refractive slabs creating phase difference or creating path difference, optical path length concept. This is another good question to understand, variations from the standard YDSE setup. It's important for your JEE advanced type of paper. Whereas for JEE mains, you can just rely more on the direct formula based questions from standard YDSE. Alright, people. So hope this question is clear to all of you. Next up, we will discuss question number 36. Wait, before that, one more question. Uh, yeah, question number 33 we will discuss. One of the parts. Okay. Then we will come to, we have to discuss refraction due to a thin film and some questions related to that. Okay. And I will also discuss the briefly, I will discuss the Byprism experiment to you, the Fresnel's Byprism experiment. Okay, people. So hope this question is fully clear. So I will just yes, just give me a minute. I will show you the whole calculation once. Yeah. So this is the part where we calculate the path difference for light coming from two sources like this, the three sources rather. Okay. So of course, this statement here, as you can see, is because A, B, and C are in phase themselves. Okay, they are monochromatic coherent sources which are in phase. Okay, Shreya, can you send me that question once more? I will discuss it. I might have lost that question unfortunately because keep receiving a lot of messages on WhatsApp. So okay. In the meantime, let's come to next question number 33. So let's look at the experimental setup in question 33. If you have HC Verma, you can just go through it yourself and start working it out. Okay, so this is okay. So I will go through that question. Okay, just give me a moment. Okay, so yeah. So there is the standard two slits here, S1 and S2, whereas in the middle wall, okay, we have one slit here and another slit here. We have a total of four slits, S1 and S2, which are symmetrical with respect to our symmetry point on the screen here. This is the screen, and these are opaque walls. So these two are labeled S3 and S4. And now this is the standard distance D, okay, where these two are symmetrical, but this distance is labeled as Z. Okay. And you have the standard monochromatic coherent light of wavelength lambda, which is incident, illuminating these two slits. So these two slits now illuminate these two slits, and ultimately any point on the screen receives light from S3 and S4. Okay. So what we have to do here is that we have to find the ratio of maximum to minimum intensity on the screen. So we have to find the ratio of maximum intensity to minimum intensity of light on the screen. Okay. Given, let's do one of the parts of the question. So the C part is that the value of Z is equal to lambda d by 4d, 4 times small d. And of course, the most important detail here that this distance capital D and this distance capital D are the same. And of course, capital D is very large compared to lambda. Capital D is very large compared to small d. So this is the thing. Okay, now we have to also assume that S1 and S2 are slits of equal width. Okay, so all four slits actually. So we'll assume that. Assume all four slits S1, S2, S3, and S4 are of identical slit width. Okay. So as a result of that, what is happening here is that the intensity of light that S1 and S2 individually produce at any point on this wall. Okay, let's call this wall A and this one wall B. Okay. So because S1 and so what is happening here is because S1 and S2 are of identical slit width. Okay. Therefore, what is happening is that the intensity of light produced by them by S1 and S2 individually, okay, at any point on the wall B is same. Okay. And let's say that is equal to I, suppose. Okay, so therefore the net intensity at the position of S3, let's say that is I3, will be equal to 4I, correct? Because it is phase difference of 0. But now what about the net intensity at the position of the fourth slit S4? Now, this one is S4, this one is S3. Okay. Why the phase difference is 0? Because S1 S3 was equal to S2 S3. So path difference is 0. So phase difference is 0. But at the position of S4, what is happening? The path difference, which is S2, or in my diagram I've taken S1 as the one below. So S1 S3 minus, rather S1 S4 minus S2 S4, ये पाथ डिफरेंस कितना हो जाएगा? That will be your small d sin theta, which is approximately d into z by capital D. So it will become like this. Okay. So now you bring in this quantity which is given here. So that path difference at that point is becoming small d by d into z, which is given to us as lambda times capital D by 4d. So it is lambda by 4. So that means the phase difference is pi by 2. Okay. So we could have also used the shortcut concept over here. We could have seen that here on the wall B, the fringe width W, let's say, okay, that is d lambda by d. Na? Okay. So therefore, at z equal to d lambda by 4d, that is 1/4 of fringe width, the phase difference directly is 2 pi into 1 by 4. So we would have come to this step directly. This is the shortcut method. So all this lengthy calculation was unnecessary. So we understand that on the screen at any point z divided by fringe width is the same thing as path difference divided by this thing lambda, which is the same thing as phase difference divided by 2 pi. So we could have used this shortcut relation. Okay. So anyway, we are getting the phase difference as pi by 2. So that means the net intensity at this point only at S4, the net intensity at S4, let's say that is I4, that is becoming 4I cos square pi by 2 divided by 2. So it's becoming 2I. Okay. So remember that formula, the net intensity in general is I1 plus I2 plus 2 times root I1 I2 cos delta phi, and that becomes 4I cos square delta phi by 2. So this very critical formula in YDSC. Okay, when I1 is equal to I1. So that is what is happening here. We are assuming the individual slits S1 and S2 are of same width, so they are creating intensity I each. So that is why at the position I3, the maxima is there, so it's 4I from this. But at this position, I4 is becoming 2I. Okay. So now the two slits which are illuminating your screen, they are S3 and S4, and they are of individual intensities 4I and 2I, or their intensities are in the ratio 2:1. So we will use that fact to find out the ratio of maxima and minima on the screen. Okay. So hope you followed the part up to here. Please ask me if there are any questions, and we'll discuss the final calculation of the ratio next. Okay, so hope this part is clear to all of you. Let me see if I can include the diagram and so now you can see the two slits which are illuminating your final screen are S3 and S4, and they are having how much intensity is 4i and 2i. So they are going to produce constructive interference where we are going to have to use this above formula, I1 plus I2 plus 2 root I1 I2 cos delta phi, where cos delta phi will be 1, and destructive interference where cos delta phi will be minus 1. So once we have got this, now we can see the next thing, which is the final part of the calculation, is that therefore the screen is illuminated by S3 and S4's interference pattern. Okay. So therefore, on the screen, the maximum intensity will be I3 plus I4 plus 2 times square root I3 I4. Or you can write that as root I3 plus root I4 whole square, where cos delta phi is 0. Okay. And the minimum intensity is I3 minus, sorry, plus I4 minus 2 times root I3 I4, or you can write that as this also. Okay, that is where cos delta phi is minus 1. So this one here should be plus 1. Okay. This is because on the screen the net intensity at any point is given by this. Okay. So now we had seen that I3 was 4i and I4 was 2i. Therefore, ratio of I max to I minimum is simply going to be square root of 4 plus square root of 2 whole square plus square root of 4 minus square root of 2 whole square. So it is going to be like this. Okay. And rationalize the denominator, and anyhow you can just do this calculation. Yeah, so they've done a bit of approximation. This will come out to be 33.92. So they've approximated and given the answer 34. If you take root 2 as approximately 1.41, you will come to this conclusion. Okay, Aditya, so bit of approximation is done in the answer. Okay, so as I told you, like, most of these things, if you have those formula in your fingertips, these questions are simple enough to work out. Okay, so not only the formula of relationship of position on the screen with respect to path difference with respect to phase difference. Okay, so fringe width formula and all that, but also the formula for the net intensity. Okay, this also becomes important. Okay, so moving on, next let us look at the interference due to thin films and some of the questions related to that. So when we have a refracting slab or like a film, it can even be like a film of oil on the ground, that kind of situation, or it could be like a thin sheet of glass, but transparent, of course. So remember, anything that is transparent is also partly reflective. So part of the intensity of light which is incident on it reflects, and part of it transmits through. In fact, these are called the reflectivity and transmittivity, or the reflective coefficient and the transmission coefficient. So let's say the thickness of this is d, and this is having refractive index mu. Okay, so this is a transparent sheet kind of thing. Okay. So when light of certain wavelength, or for that matter any light, is incident on it, what happens is that out of the incident light, a certain percentage of light transmits and a certain percentage reflects back. So certain percentage of intensity will reflect here, and certain percentage will transmit and then reflect back. Okay. So if I draw more sort of magnified diagram of what is happening over here. So out of the incident beam, certain amount of light is reflected back here, but certain transmits in and then is reflected at the second surface. There is also, I mean, not all of it is reflected, so there will be some absorption also. Okay. So in a typical situation, what happens is that certain percentage of light is reflected, certain percentage of intensity of light is transmitted, and only certain percentage is reflected back. Okay. So now if we assume that this is on the ground, okay, so this is actually, we'll come to a situation where it is having air on both the sides, but let's say right now I'm assuming that this is on some opaque surface, like on the ground. Okay. So what will happen is that if the incident light is of intensity I naught, okay, then let's say alpha I naught is the intensity reflected at the surface 1, let's say. So this is our surface 1. So alpha is a factor less than 1, which is called the reflection coefficient. Okay. And what will happen is beta I naught will be the intensity of light transmitted. That is this. This is reflected, this is transmitted, and this again reflected from below at the second surface. Okay. So here beta is also less than 1, and it is called the transmission coefficient. Okay. And in general, what we say here is that 1 minus alpha minus beta, this is, let's say, gamma, which becomes the absorption coefficient. Okay. So for example, if alpha is 0.4 and beta is 0.3, that means that gamma will have to be 0.3. Okay, because the remaining percentage of the intensity of light, the remaining energy is getting absorbed. So in general, when light is incident at any surface, there are the three phenomena that happens: reflection, transmission, or refraction, you can call that also. Okay. And and absorption. So basically, in general, for light incident on a transparent medium surface, okay, certain percentage of intensity is always reflected, transmitted, okay, and also absorbed. And the sum of these three must be equal to the 100%. Okay. So now anyhow, similarly at the second surface also, a certain percentage of the incident light, that is of intensity beta I naught, because that's the transmission coefficient, okay, is reflected. Okay. So finally you can see that there is, for an observer who's seeing from here, there is light coming back, partly reflected at surface 1 and partly reflected at surface 2. And between those two beams of light, reflected at surface 1 and surface 2, there is a path difference, which is actually an optical path difference, because the light reflected from the second surface has traveled an extra distance of 2d, twice the thickness, but in the refractive medium of mu. So the optical path difference is 2 times mu d. So that creates phase difference. Okay. Now the thing you have to be very careful about in these questions is whether or not you have to consider the phase inversion from reflection. So obviously, yes, you have to consider phase reflection, but in the example that I have taken, for example, the reflection at surface 1 is also a rigid boundary, because mu is greater than 1. The reflection at surface 2 is also a rigid boundary because the ground is even more rigid, or the speed of light in ground is tending to 0 because it's absorptive in nature. So both the reflections are resulting in phase inversion, not contribute to phase difference for the interference. Yes. So I remember somebody in your class had asked me why the phase inversion of reflection is not taken into account in thin films. It's not that it's not taken into account, but if you're considering the thin film to be on a rigid surface, then both the reflections at the first surface as well as the second surface involve phase inversion. So ultimately, the phase inversion does not contribute to any net phase difference between the reflected beams from surface 1 and surface 2. So hope this point is clear over here. So we'll just make a note over here. So now coming to the important calculation part. So what we can understand finally is that for incident light normally, okay, okay, the reflected light is a superposition which will of course result in interference of light reflected at surface 1 and surface 2. Okay. So the optical path difference will be twice of mu into d, where d is the thickness. Okay. And the phase difference will be 2 pi by lambda into optical path difference. So the phase difference delta phi will become this. Now this way we also understand that since both the reflections at surfaces 1 and 2 are reflections from rigid boundaries. Okay. So both involve phase inversion. Okay. Therefore, there is no contribution to the phase difference delta phi from phase inversion. Okay. So that's why the net phase difference is just 2 pi by lambda into this. Okay. So for example, let us look at question 35, okay, which is one of the questions you have asked also as a doubt. 35 and 37. Let us discuss these two questions. So before that, if 2 times mu d is n lambda, we will have constructive interference. And if 2 times mu d is n plus half lambda, we will have destructive interference. Okay. So this is the standard thing to remember about this. So now coming to H.C. Verma question number 35. So it says that we have a soap film whose thickness is 0.0011 millimeter. Okay. And it appears dark when light of wavelength 580 nanometers, which is basically something like sodium vapor lamp. Okay. So this produces destructive interference. And it is given to us that the refractive index is, so we have to find mu, given that mu is in between 1.2 and 1.5. So this is that type of question where that numerical analysis becomes important. Okay. So the condition we have to apply is for destructive interference, this one. Okay. So just give it a try. 2 mu d should be an odd multiple of lambda by 2, where lambda is 580 nanometers. Okay. Such that mu is greater than 1.2 but less than 1.5. So how will you come to the exact conclusion of what mu is? Bit of numerical analysis has to be done. That number theory thing, with odd number concept coming in here. So just try this out, people, and if you finish this, you can go through 37 also. We'll discuss both these questions. Yeah, good, Aditya. So you work this out. So basically, we have to apply this concept now that 2 times mu into d is equal to n plus half lambda. So from this, we are getting the formula for mu to be some odd multiple of lambda by 4d, like this. Yeah? So that is some odd multiple of lambda, which is this much, upon this, which is, let me see, 11 into 10 रेज पर ये कितना हो जाएगा, 4 minus 4 minus 3, so minus 7. Okay. Okay, now next what you do is you keep putting these odd numbers as 1, 3, 5, 7, etc. and see when you get something in between these two. So I think you will get something close to 1.3. Okay, now similarly, let's look at the 37th question. So it says a parallel beam of white light is incident normally on an oil film which is of given thickness. So this is an oil film whose thickness is given to us as point. Okay, so it's very thin. 1 into 10 raised power minus 4 centimeters. That's actually 1 micron thick, 1 micrometer thick. And refractive index of the oil, actually it's a water film, sir. My mistake is so. So refractive index of water we are taking as the standard value 1.33. Now what is happening is the light incident is white light. Okay. So the wavelengths are standard between 400 and 700 nanometers. So we have to find out strongly transmitted. So here what we mean by transmission we have to understand. So this is like a film of water which is suspended in air. So this is where the question becomes a little bit more interesting. There's air on either side, and we are talking about light which is transmitted through the water film. Okay, so there is air on either side and water in between. So transmitted light will be basically light which is coming out on this side. Okay. So it is light that is directly coming out or light which is doing this. It is reflected and re-reflected. Okay. So interference you have to consider between light directly transmitted and light. So if we take this as a surface 1 and this as a surface 2, so light which is transmitted at surface 1, okay, then reflected at surface 2, and then again reflected at surface 1. So these are the two types of light that we have to consider. Yes, so here an extra difference of 5 would be considered. Okay, so let's understand. Let's compare these two. I understand. So one, we are considering light which is going through directly, and the other we are considering light which is going through, then reflected, then again reflected, and then going through. Okay. So for the second one, you can see that this is having an optical extra path length of 2 mu d. Okay, but the phase difference will be equal to 2 pi by lambda into optical part difference plus or minus of pi, because one of the reflections is going to be a soft reflection, the other is going to be a hard reflection. Okay, so this relationship holds because reflection at surface 2, okay, there is no phase inversion, but reflection at, oh sorry, so both the reflections are soft, so there is no phase inversion, my mistake again. Okay. See, when light is coming back and reflecting here also at surface 1, again no phase inversion. Okay, because see now both of them, the reflection is such that there's air on the other side and water on the inside, so it is reflection of a lighter medium. The medium on the other side is lighter, so there's no phase inversion. Okay, so it's just this much. Okay, so therefore the strongly transmitted ones, we want delta phi to be 2 and pi for constructive interference. That is for strong transmission. Okay. So here also the phase difference, phase inversion doesn't play a role. I'll show you an example where phase inversion plays a role, but here it does not play a role. Okay. So the condition is that this delta x optical, which is 2 times mu d, should be equal to n lambda. So the wavelength should be in this region, 2 times 1.33 into 10 raised power minus 6 divided by n. So we have to look for those values which fall in this region, or okay, so 2.66 by n should be between 7 by 10 and 4 by 10. So look for those values of n. Okay. And from that you calculate the wavelengths. So you see that if you take n equal to 1, obviously it doesn't fit the case, okay, because 2.66 is greater than zero point 0.7. If you take n equal to 2 also it doesn't fit the case because 1.33 is greater than zero point 0.7. If you take n equal to 3 also it doesn't fit the case because you get zero point 0.8 something, no? 0.89 something, so that is greater than zero point 0.7. But you take n equal to 4, okay, so I think that will fit the case. Yeah, you get 0.665, which is less than zero point 0.7 and greater than 0.4. Then you take n equal to 5. So this is also fine. 0.53. Like this, okay. Then let's see for n equal to 6 what we get. So 2.66 divided by 6. So that's just about falling in the boundary region, 0.443. So this is also falling in this region. Okay. But n equal to 7, I think, will again come below zero point 0.4. You get 2.66 divided by 7. That will be 0.38. So that is less than zero point 0.4. So this is also okay. So these are the three values of n. So corresponding to three values of n, we will get one wavelength, we'll get the second wavelength, we'll get the third wavelength, and those wavelengths will be given by this formula above. Okay. 2.66 upon 4 into 10 raised power minus 6. So that will give us 665 nanometers. Nearly 666. Okay. Then 2.66 divided by 5. That will give us that 532 nanometers. So these are the strongly transmitted wavelengths. So this will give us that 443 nanometers. So these are the transmitted ones. Okay. I'll show you an example where the phase inversion comes into play, but in this transmission case, it doesn't come into play. Okay. If we were seeing the steam film from above and we were seeing it reflected light from above, then phase inversion would come into play, provided there is air on both the sides. Okay, now, so as I was telling you, let's look at a situation where phase inversion does come into play, and that would be something like this. You have that same water film or thin cellophane film or something like this, but it's got air on either sides. So it's hanging in the air basically. And you're not looking at transmitted light, but you're looking at light reflected from one side. So this is a film of thickness d, refractive index mu. Okay. But on either side of it, there is air. So now when you see light incident here, normal incidence, and you look at light reflected back, so the observer is on the same side. So this time for reflected light, okay, there is interference between light reflected at surface 1, okay, which involves phase inversion, and surface 2, which involves no phase inversion. Okay. So now what will happen is that your net phase difference will become 2 pi by lambda into optical part difference plus or minus pi. Whatever we write it doesn't make a difference. Okay. So delta x optical, which is 2 mu d, it should be n plus half lambda for constructive interference now. This becomes a condition for constructive interference. Okay, phase difference will become 2n pi, or in this case 2n plus 1 pi, whatever. And or we can write this as minus 1 pi. And n lambda for destructive interference. Okay, so this is the variation case to remember. Okay, guys, so this is about your single, interference at thin film. Okay. Now, next thing we will discuss is the Byprism experiment, and I'll show you an example or two of calculation in that. Okay. As it is a variation of YDSE, very similar to the case we had taken of the lens cut into two, and making use of the lens to create two virtual secondary point sources which are coherent. Okay, so let's take a quick 5-minute break and we'll discuss after that. Samik, explaining to you. So see what is happening here. This is like a, think of it like a cellophane film or a water film or something which is in air. So on either side there is air beta. Okay. So what is happening here is that the light which is incident on the top surface and reflects off the top surface, जो यहाँ पे reflection हो रहा है, this is reflection at a hard surface, so there is phase inversion. Okay, but the light which is transmitted through this and then reflected here, now here what is happening, on the other side there is air, so here there is no phase inversion. Okay, so at surface 1 there is phase inversion, but for reflection at surface 2 there is no phase inversion. So ultimately the interference is happening between light reflected at surface 1 and surface 2. So the phase difference involves not only the optical part difference but also the phase inversion. Is it clear, Samik? Okay. Okay. So people will take a quick recess of 5 minutes and then we'll discuss about the Byprism experiment. Okay, students, so let's resume. Just give me a moment. I will reshare the whiteboard. Okay, so next up, as I was saying, we will discuss in particular, what is called the Fresnels or Fresnel's Byprism Experiment. So this particular experiment has the name of Fresnel's Byprism Experiment. Okay. So the way we draw the apparatus is going to be a little bit different than the actual apparatus because it involves very very thin prisms. So it's a little difficult to draw prisms which are actually that thin, but we will have to do some approximation while understanding the calculation part. So the experimental setup consists of like two right angle prisms which are extremely thin, which I'm not able to show as extremely thin. So I'll show them like regular prisms like this. But if you just imagine that they're very thin, which are placed against each other. So almost they become like a single prism like this. So in many versions of this experiment, actually there aren't two separate prisms, but one single prism that is carved out of some material. It's like this. So okay. And then you have that standard kind of situation where you have an opaque wall. And you have a screen on the other side at a very large distance, on which you observe the interference pattern. So this is just a symmetry line. So typically this distance here is a known quantity. This distance is a known quantity. And you of course have a very narrow single slit here. So this is the basic experimental setup. And you have monochromatic light coming from a monochromatic primary source which illuminates the slit of wavelength lambda, let's say. Okay. Now this is the biprism, which is basically two right angled prisms. Okay. Now they are of very small angle A. each. So angle is typically of the order of 1 degree or less. Very, very small angle prisms. And refractive index mu each. Okay. Joined together, at the base, that kind of thing. Okay. So this single slit now acts like a secondary monochromatic source. So it's creating your coherent monochromatic light. But light reaching the screen is going via two paths. At any point on the screen, light will come via the first prism and via the second prism, and will travel different optical path lengths. Okay, so that creates the interference. Okay. So, so firstly, the slit S is of thin slit width, okay, of the order of lambda, like you have in YDSC, that kind of slit. Okay, so that slit acts as a monochromatic secondary source. Okay, producing coherent monochromatic light. Now, the light at any point on the screen comes from interference of light via two paths, via refraction from prism 1 and refraction from prism 2. So that is what creates the interference effect. So let's try to understand how the interference of light exactly, or rather how the deviation of light to begin with exactly happens. So coming back to the setup, okay, what exactly the prism does, it deviates light, and we can use that approximate formula of deviation. So imagine light which is nearly normal over, I mean nearly parallel to the principal axis over here. So this prism will tend to make it deviate in which direction? Tend to make it deviate like this. So this incident light, if you compare it with this, this angle of deviation is delta, and it appears to be then coming from. You have to remember this is a very exaggerated diagram. Actually, this is a very, very thin prism, so this deviation is very less. So it appears to be coming from some S prime here, let's say. Okay. And now any other beam of light also, like here, this will also tend to deviate in such a way that, so imagine that these are all nearly parallel. I'm showing them as very, very divergent beams, but you have to imagine that this angle is actually negligible because we are considering very thin prisms. So this deviation is also delta. And you remember the formula for delta, mu minus 1 into E for thin prism, approximate formula. So light coming via the first prism appears to be coming from this virtual source S prime. Yes, it will give us interference. Okay, so as you can see that these kind of beams, they are incident everywhere on the screen over here. Whereas similarly, if we consider beams of light incident on the second prism, so for example, you start with a beam that is incident over here. Now this will tend to deviate in the opposite kind of sense, like this. So this will appear to be coming from somewhere here. Okay. And you can see that this is, let's say, S double prime. So here the deviation is like this, same delta. Okay. Or another beam of light incident somewhere here will, after deviation, appear to be coming from same delta for both the sides. So basically, S prime and S double prime act like the two virtual sources, and all this light you can see, these light beams, they are all superposed. So there is a certain region on the screen where light from both the prisms is superimposed. So that creates interference. Okay. So this is happening. Interference of light from prism 1 and prism 2. Okay. So S prime and S double prime become two virtual coherent monochromatic sources. Okay. Now, if you take the distance between S prime and S double prime as small d, and if you take this as capital D, the fringe width on the screen will come from that same formula d lambda by d, such that the fringe width is this, where d is equal to a plus b, and small d we have to see how to calculate. So we'll discuss that next. Okay. So actually, in the original experiment, small d is calculated experimentally using a lens and all that. Okay. Know this because this is part of the experiments that you do in typically in first year BTech in your physics course. But here there's also a way of doing an approximate calculation of small d from A and delta. So we'll discuss about that also. Okay, so for the calculation of small d, the approximate calculation method that we can use is again coming from that angle of deviation concept. So for that, what we do is sort of follow this ray diagram. So now if we are considering light from this slit, so first let's draw the symmetry line. Okay. So now let us consider light which is nearly parallel to this symmetry line or symmetry axis. So it's nearly parallel like this. Okay. And after suffering deviation here, I mean something like this, let's say. So again, remember this is a very exaggerated kind of picture. Actually, the deviation is very small, less than 1 degree, because the angle of the prism itself is about 1 degree. So anyhow, so produce this back, this this refracted ray produced back, or this emergent ray produced back, gives you the position of S prime. Okay, this was the position of S. So this is the angle of deviation here, this delta, which is the same as this angle here, delta. Okay. And this distance here will become d by 2, because you have the other one here. This is also at d by 2, and this was a. So delta you can see is mu minus 1 into the angle of the prism, and you can see that tan delta is nearly equal to delta, equal to d by 2 divided by e. So d becomes 2a delta, or d becomes nearly 2a into mu minus 1 into the angle of this. So from that we get the fringe width formula. Yes, yes, Somiti, that's correct. Very good. Okay. However, when you do the experiment, in part of your BTech first year or any other physics course you do, you will see that this is not the way small d is worked out in the experimental method. It is actually you use a lens to calculate small d. Okay, so I'll just show you a small example of that. Okay, so again for your your level of questions at JE level, this is what you require. So should be enough. But just for your self interest, I'm showing you the original experimental manual that you have for this, which is like this. So the experimental setup consists of these things. The apparatus, it consists of, as you can see here, a sodium vapor lamp. Okay. So you have the sodium vapor lamp which is producing the monochromatic light of wavelength lambda, and you have that single slit over here which is going through the biprism, and we also make use of a lens. I'll show you where. And we make use of an eyepiece, and there's an optical bench which is used to accurately measure the distances, okay, between the different things and all that. Okay, so how this works out is, let me take you to the, yeah, so this is the diagram of the actual experiment. So as you can see, this is what is happening, same way we had just discussed. Okay, so light is actually coming from this single slit acting as the source. Okay. But because of the deviation of light, you have these two virtual sources S1 and S2. So the light reaching this portion of the screen is receiving light from both S1 prime and S2 prime. So there is this alternate dark and bright fringes, and this is the formula of the fringe width. Basically, they are using the symbol beta for fringe width, d lambda by small d. You can see in their diagram, this will be small d, and this will be capital D. This one will be capital D. Okay. So now, see, they've given that S1, S2. This is the distance between the two virtual sources, small d, and capital D is the distance between the screen or the eyepiece. So basically, you place the eyepiece over here, and as you take the eyepiece up and down, the eyepiece receives bright light versus dark light versus bright light. So by taking the eyepiece up and down, you can measure how much distance you're moving along the screen. And as you're moving along the screen, your light intensity is changing to bright to dark to bright. So you're able to measure the fringe width. Okay, so that's how beta is measured. So beta is one of the things which is measured. The other thing is small d is measured separately. So this experiment is to actually calculate lambda. The purpose of the experiment, when you do it at the BTech level, will be to basically observe or to find out the value of lambda. Okay. So objective of the experiment is to determine the wavelength of the monochromatic source. Okay. So everything else has to be measured from the experiment. So coming back to that formula, so here you have to find out the value of lambda from measurement of these things. So how we measure the fringe width? Okay. So there are some additional things which I won't get into here. So measurement of fringe width, so that eyepiece that we are talking about, that is moved along the screen such that as it moves from dark to bright fringe. Okay. Now to minimize the experimental error, we always count a large number of fringes. So we count something like 10 fringes at a time and measure the distance between them, and then divide it by 10 to get the fringe width. So that's how that beta fringe width is measured. Now let's come to the measurement of small d. So in the original experiment, small d doesn't come from that formula of 2 times a into mu minus 1 into that thing. It doesn't come from that. It comes from actual measurement. So what we do is, without changing the position of the slit, okay, and the biprism and the eyepiece, a convex lens is mounted on the optical bench. I'll show you the diagram also. And the distances d1 and d2 of the two well-defined images of the two slits are measured with a micrometer screw by this. Okay, so what we do here is this. So you keep the slit in its place. You don't actually change the position of the single slit. So that is in place. You keep the biprism in place, and you keep your observation screen and all that in place with a micrometer for the eyepiece to observe. Okay, but now you place a convex lens in between, and you always take the convex lens such that this total distance capital D should be about 4d, 4 times its focal length. Okay, so then you are able to observe the situation well. So you will see that, like the experiment for measurement of focal length of convex lens, okay, there are two positions, position 1 and position 2. There are two positions at which, from your eyepiece, you will clearly be able to see the images of S1 and S2. Okay, and those will be such that these distances here are d1 and d2. Okay, so you'll be able to see this slit through prism 1. It will appear to be at S1, and you'll be able to see this slit through prism 2, and it will appear to be S2. And when you see it at, for example, this position here, the first position, okay, then you can see that you're looking at this and this. So you're measuring this distance, which they have taken as d1. Okay, so d1 basically comes from this UV formula. Okay. And similarly, when you are at position 2, you will observe them here and here, and you'll be able to observe this distance as d2. So either by using this formula or the inverse of this formula, because u and v become inverted, so you have d by d2 is equal to v by u. So if you eliminate this and this, you can see that d becomes square root of d1 d2. So by measuring d1 and d2 through the micrometer, because you're moving the eyepiece micrometer up and down. So you're able to measure the distance d1 for the position 1 and the distance d2 for the position 2. You're able to actually measure small d and put it back in that formula that fringe width beta is equal to d lambda by small d. Okay, so from that you find out lambda because beta is measured, small d is measured like this, and capital D is measured on the optical bench on which you placed all this. So that is the original experiment. Okay, so if you guys like, I will send you this manual also, though it is actually part of BTech first year manual. Okay. So the details of this experiment are not that much important for you. Okay. But for example, the original apparatus you will see here, it says very clearly that each of the refracting angles is 1 degree or less. And in practice, the biprism is constructed from a single plate of glass, suitable by suitably grinding and polishing, with an obtuse angle which is only slightly less than 180 degrees. So that kind of thing. And then, of course, a lot more details is there about the eyepiece and optical bench and how to remove the parallax error and things like that. So, this is about the biprism experiment. Okay. Now, one more thing which you would have noticed in questions also about single slit diffraction. So we've discussed about single slit diffraction earlier. Now there's a variation of that single slit diffraction where you have diffraction through a circular aperture. So we had seen in single slit diffraction experiment, okay, if we had a slit width of A like this and monochromatic light of wavelength lambda incident, then on a very far away screen we got an intensity pattern which was that sine square hyperbolic kind of pattern. Okay. So we had seen like this that at any angular position theta on the screen, we got I is equal to I max sine square beta upon beta square, where that beta was equal to this thing, pi by lambda into b sine theta. Or from the symmetry point, this point is at a distance y. This kind of thing. But this distance was, sorry, this should be, instead of b, it should be a. The slit width basically. So this was the thing. So we got, for example, the position of the minimas. Minima was the position where beta is equal to pi 2 pi, like this n pi. So basically E by lambda sine theta was equal to n, or theta is equal to sine inverse lambda by a sine inverse 2 lambda by a, and like this sine inverse n lambda by a. And remember, for a standard this kind of single slit experiment, a is typically of the order of 50 lambda. So a bit wider compared to the YDSC setup, but still very small compared to, I mean, still a very narrow slit width. Nothing like a micrometer or anything like that. Okay, so this was the standard single slit experiment. Okay. Now in this you understand that three-dimensionally what is happening is that on the wall you have a slit like this. This is the slit. Okay. And therefore on the screen in front, what you are seeing is alternate bands of bright and dark light. So you're seeing bright and dark fringes, bright fringe, dark fringe. right side. But if we change the geometry to a circular aperture, okay, so then there is a slight difference in the formula as well as the geometry. So diffraction from a circular aperture. Okay, let us look at this. Okay, so here we are talking about this kind of a setup where you have a round hole like this in a wall, and on the other side you have the screen, and you have monochromatic coherent light incident from this side. So then what you see on now the round hole. So this is a opaque wall with a circular aperture, and this circular aperture has a diameter of E, let's say, where E will be of that order of magnitude, 50 lambda types for the monochromatic light of wavelength lambda, which is incident. Okay. So what we see on the screen as a result of this kind of situation is diffraction rings. Okay. So this is called Fraunhofer diffraction. This experiment is called Fraunhofer. I think this is how it is spelled. Okay. So we see diffraction rings on the screen. Okay. With like we see a central maxima that is like a bright disk of light. Then first minima is a dark ring around it. Okay. Then first maxima is a concentric bright ring, and so on and so forth. Okay. So this is the diffraction pattern. So just make a quick note of that if you like. Now then there is a formula related to this which we'll discuss, which is of significance for us. So by the way, this is part of JEE main syllabus only, because anything to do with diffraction, okay, single slit diffraction as well as Fraunhofer circular aperture diffraction is not going to be asked in JEE advanced. This is purely JEE mains. So also you can expect the questions to be only formula based. Okay, so the important formula to remember here is the formula for the radius of the first dark fringe. Or actually, the formula of the angular position of the first dark fringe. Okay. So let's understand that geometrically first. So making a slightly more side-on kind of diagram now. So if this is your round hole, okay, and then on the screen you're seeing rings of light like this. So for the first dark fringe, for the first minima, the angular position. Okay, so with respect to the symmetry line, angular position of the first dark ring or first minima is given by the formula sine inverse 1.22 lambda by E. Where remember E is the diameter of the circular aperture. Okay. E is the diameter of the single circular aperture. So in single slit diffraction, you remember the formula of the first minima was sine inverse lambda by E. This was single slit diffraction. So here you just remember that there's a factor of 1.22 involved in front. And that comes because of the geometry of the circular aperture compared to the slit, which makes the wavefronts kind of semi-spherical, the wavefronts that we are considering. So it complicates the geometry, and without getting into that complex three-dimensional geometry in spherical coordinate system, which we cannot do mathematically, it's a bit too complicated for us. We just memorize it as an empirical formula or a formula that comes from experiment. Okay. So of course that also means that if this distance between the two screens, capital D, is very large compared to E, okay, then we can take for D very large compared to small a, theta is a small angle. Okay, so theta can be approximately taken as tan theta. So the radius R of the first dark fringe or the first dark ring becomes equal to 1.22 lambda d divided by E. So we can replace sine theta or theta with tan theta, which is nothing but that radius divided by capital D. Replacing that in the first formula, get this radius of the first dark ring. So this is a formula you will have to memorize. Okay. Now the next place this formula becomes significant is in a property of lens, convex lens, called the resolving power of a lens or limit of resolution. So this is particularly useful in construction of telescopes and uh, such devices where objective lenses are used. So resolving power of a lens and something called Rayleigh Criterion. So the basic concept of this is something like this. When you consider typically the objective lens of telescope, it's basically a convex lens which is used to create the image of a very distant source of light like a star or something on its focal plane. So this is a converging lens whose focal plane is this one. Objects kept on this side, and this is the principal axis. So what will happen is at a very large distance, very large compared to the focal length. If there is, for example, a source of light S1 over here, its image will be formed over here, S1 prime. But if there's a source of light here, let's say S2, its image will be produced somewhere here, S2 prime. Okay. Now, in terms of light as a wave phenomena, what is happening is that the light coming from these two sources is going through like a circular aperture of the lens and is forming a diffraction pattern over here actually. So what you end up seeing for very distant sources is a diffraction pattern of light where the intensity of light is like this. So you don't just see a point image, but you also see diffraction rings around it. So for the two to be distinct, for the two images to be distinct, the ring should not overlap with each other. Otherwise, you will not be able to resolve the two images, okay, properly. So just a second. So I'll make an approximate diagram here. So what is happening is that this angle and this angle are nearly the same, because that's what happens for an object placed over here. The light ray through the pole of the lens typically goes undeviated. So that's the thing. So this angle theta is the same as this angle theta over here. So its image S prime is more or less at the focal plane length. Okay. So what happens is that for two very distant light point sources of light, so for two distant point sources of light, S1 and S2, okay, the images on the focal plane S1 prime and S2 prime actually contain the diffraction rings. Okay. So to resolve the images clearly into two separate light sources, okay, a certain limiting condition must be satisfied. So that limiting condition is called the Rayleigh criterion. Yeah, the line joining S1 and S1 prime is the principal axis, but S2 and S2 prime is at an angle to the principal axis. Okay. So that is the diagram. See, it's here basically it is something like this, that at the level of the lens, what is happening is that if you consider this as your principal axis, suppose if this is your principal axis, suppose now for a beam of light coming exactly along the principal axis, it goes undeviated. Okay. So if you have a very distant source of light which is very far away but lying on the principal axis, okay, then the light coming from that will be parallel beams which are very close to the principal axis. So this is like the light coming from the source S1 which was lying on the principal axis. So its image will be formed where? Its image will be formed on the principal axis only, but at the focal plane. Okay. So this is like the approximate ray diagram. So the light coming from the source which I had shown as S1. Okay. So this is from a distant source S1 on the principal axis. Okay. So its image is formed S1 prime on at the focal length. But what about light coming from a second source which is not on the principal axis, okay, which is slightly above the principal axis? So for that again it's a little difficult to show in this diagram because we want to show an angle which is tending to zero. So we will do a sort of approximation. So if this is your principal axis, the light coming from that second source is at a slight angle with respect to the principal axis. So imagine that very distant star or whatever, which is at some angle with respect to this. So the direct beam of light coming is like this. The one going through the pole will be undeviated, but these rays, they will after refraction bend slightly like this and give you an image of it. So I don't know why this is happening. So this is giving you an image on the focal plane, but at S2 prime, like this. Okay. So now if you just follow the ray which is going through the pole, this one, you'll see that this angle is the same as this angle. So that is why we say that if we have an object which is over here, its image will be formed somewhere here, where this angle will be the same as this angle. Is this clear, Shreya? Okay. This is from distance source S2, which is at angular deviation theta with respect to S1. So from the position of the lens P, if you look at the two sources S1 and S2, their angular separation is theta. Okay. Now what happens is that their image's angular separation is also theta, and if that theta is so small that the diffraction rings overlap each other. Okay, so now imagine at the screen, okay, what is happening is that this is the central maxima and this thing for the image of S1. Okay, and let's say the image of S2 is such that it's like this. Okay, then what will happen is that these images will tend to overlap. Okay, which is the reason why, in the night time, if you observe, for example, a car coming from a huge distance, initially its headlights appear to be merged like one light, but only when it comes closer to you, the angular separation is large enough that instead of this, what is happening, instead of overlapping, they are separate enough. So it is all about the angular separation between the first and the second image. If it is something like this now, and the second one is here, and the first one is here, now they are separated. These images are resolved into two separate sources. Okay, so it all depends on the angular separation. From the position of the lens, it all depends on the angular position of the first and the second. It all depends on this. So the Rayleigh criterion is that this theta should be the angular separation between the first and second should be such that the first one's minima is inside of the second one's central maxima. Understand? So the central disk of the second one should be outside the first dark ring of the first one. S2's central bright disk should be outside of S1's first dark ring. So theta should be greater than 1.22 lambda by A for resolution, for resolved images, where A is the diameter of the lens's aperture. Okay, so theta is, sorry, A is this diameter. So the size of the lens becomes important. So this particular formula here, this is called the, or this particular concept is called the Rayleigh criterion. Okay, so as the distance between the two sources and the pole of the lens is decreasing, so imagine you're talking about your eye lens and a pair of headlights coming closer and closer to you. So as the headlights are coming closer, the angular separation between the two headlights is increasing. So the moment the angular separation becomes 1.22 lambda by A or more, your eye is able to resolve it into two separate sources of light. But before that, they merge into one single source of light because of this phenomena, and diffraction is part of it. Yeah, Shreya, now about, I think your doubt had to do with that binding energy per nucleon. Na? So it appears to me something is wrong with the language of the question. The question clearly says is calculate the binding energy, not binding energy per nucleon. So you have to calculate the mass defect and just multiply it by c square, or that factor of 931. So Whenever binding energy per nucleon is asked, it should be asked separately. It's not binding energy. Binding energy means that only it is the total mass of nucleons minus the actual mass of the nucleus into c square. You don't have to divide it by the mass number a. Okay, I will send you a reply on WhatsApp also explaining the same thing, but hope you have understood this. Okay, okay. So it's probably some kind of a misprint in the question. It should have been binding energy per nucleon. If you are asked binding energy per nucleon, this the statement should ask that. Okay, because binding energy and binding energy per nucleon are two separate things. Okay, so people will be concluding here today. Now next, so let's discuss our flow chart for the next few lectures. So as I said, now only the JEE mains topics are remaining. So what I'll be doing is I'll be discussing, since we are in optics, we'll be discussing polarization of light. Okay, then we'll be discussing optical instruments, okay, namely telescope and microscope. And then we'll be discussing modern physics topics, semiconductors, and logic gates. Okay, so these are JEE mains only topics, as is diffraction. So this is what's coming up in the next couple of lectures. So I think next time we should be able to cover this portion, polarization and optical instruments. Okay. So these two we should be able to cover. Okay, so that's it for today's session, people. Wish you all the best. Until next time.